Hi there, welcome back to thinktankonline learning. So in this video we're going to verify the divergence theorem. Okay, so before we start, if you're new here, just click the subscribe button and don't forget to turn on the notification bell so that you don't miss the other videos. Okay, so if you're looking for other videos, I've got a plenty of videos where I verified the divergence theorem. Okay, so on this one we have given our vector field and also given our limits, and z ranges from 0 to 2. Okay, actually here it's 2x, and we're given that we have a cylinder with the equation x is equal to 1 minus y squared, and we need to verify the divergence theorem. So I'm going to show you the visual or the picture of this solid in 3D. This is the walls of a cylinder and we're in 3D. So as you can see, these are the walls of a cylinder. Okay, but I'm going to show you how it looks like in 2D. So in 2D, you're going to see this is not a uniform circle. The radius is going to vary from here to here. So the radius from here to here is not the same as the radius from here to here. You're going to see we have two different distances, so you have to be careful. We're not going to use cylindrical coordinates because cylindrical coordinates are too complicated, especially in this problem. Okay, so now I'm going back to 3D and I'm going to add our base z equals to 2, z equals to 0. Okay, so as you can see, this is the z equals to 0 plane. Okay, after that I'm going to put z equals to 2x. Okay, so the solid that we want to find the total flux, it is the solid between the red one. This is the red, the boundary, the cylindrical surface here, the green surface here, and the blue surface. Okay, so what I'm going to start with, okay, so what we're going to start with, we're going to start with the base. Okay, so we're going to find the total flux outside this bottom. Okay, so as you can see, as I'm saying, it's the bottom, so that means outside, that means my plane or my normal is going to be below. As you can see, this is the positive z-axis, so my normal is going to be below, so it's going to be negative k. Okay, then I'm going to find the flux out of this surface, this one, this green one. So as you can see, it's a slant, so the normal is not going to be obvious like what I just did. We're going to calculate it, I'm going to show you. And lastly, I'm going to finish with the curved surfaces. Like I always say, I start with easy things first, and then go to that one. Okay, so this is the solid you are talking about, right? This one. Okay, so that now we know what we are dealing with. First of all, we're going to start with the easiest side. So for the divergence theorem, we want just to calculate the flux, the outward flux. Okay, so I'm going to write it here. Okay, so on the right hand side we have the triple integral, which represents volume. Okay, and we're going to write dv here, which means the divergence of the vector field, and we're going to write dv. Okay, so if we evaluate this triple integral, we're going to find the total outward flux of the whole solid. Okay, but if we don't do that, we're going to do the surface integrals. So we're going to calculate the flux out of each surface, and after that we're going to add them together. So we're going to have something like this. So f n ds for the surface, and in our case we have three surfaces, s2 f n ds plus s3 f n ds. Okay, so what I'm going to start, obviously everyone will start with the east side, and I'm going to do the same. So I'm going to start with this side. Okay, so this one is not that, but it requires some time. Okay, so what we're going to do, our vector field, we have to calculate div f, which is the divergence. So I'm going to write div f here is going to be equal to what? So we know the formula. It's going to be partial x for f plus partial y f plus partial partial z. Okay, so this is partial z of f. So this is going to be fi, and this is going to be fj, and this is going to be fz. Okay, you can just write I here, j here, and c here. Okay, so now what we're going to do, we're going to find the partial x for the I component, which is y plus z, plus the partial y for the j component, which is y squared, plus partial z for the k or z component. Okay, this should be k. Okay, and we have 2z, okay, like this one. So this is going to be our divergence. Okay, so let's do that. If we differentiate here with respect to x, we're going to get 0. If we differentiate here with respect to y, we're going to get 2y. Remember, we no longer have I and j. And if we differentiate here, we're going to get 2. So that means the divergence is going to be equal to 2y plus 2. Okay, so now let's go to our limits. Okay, so some of you are told that each and every time you draw the cylinder, you're going to use cylindrical coordinates. Okay, so in cases like this, it's going to be a different case. Okay, so as you can see, we're just given the wall of our cylinder, and we're given that x squared is equals to 1 minus y squared. Okay, so if we sketch this, let's sketch this in the xy plane. Okay, so if we sketch, we're going to have something like this. Okay, so y here and we have x here. Okay, so to those who don't know this graph, I think the best way to draw this graph is just by moving y from here to here, and you're going to have the graph of y equals to 1 minus x, the square root of 1 minus x, and you know the graph of root x, and after that we're going to apply some transformation, and we're going to have something which looks like this. Okay, and we have to make sure that what you have drawn is not a circle. Okay, so this is not a semicircle. It's not a semicircle because, okay, we have one here, we have one here, we have one here. Okay, but the coordinates, the value of x here is not equal to the value of y here. Okay, you have to note that it's different. If you want, you can try it. You can just put when x equals to 0.75, and if you put x equals 0.75 here, you're not going to get the value of y being equal to 0.75. Okay, so this is not a circle. Okay, so now that means we're not going to use cylindrical coordinates. When cylindrical coordinates we are going to need the radius, but our radius is going to vary. Okay, so you're going to see that the radius is going to vary according to this value of x and y. So I'm not going to do what is complicated. I'm just going to do what is. Okay, like what Einstein says, simplicity is genius, right? Okay, so now what are we going to do? So for the z limits, we're told that our z ranges from z equals to 0 and z equals to 2x. Okay, so I'm going to write z here. Z ranges from 0 to 2x, and I'm not going to change anything here. I'm going to leave it like it is. Okay, now for x, okay, it depends on the order of integration which you want. Okay, so here I'm given x equals to 1 minus y squared, so I'm going to use that. So that means I'm going to integrate from this side to this side to this side. Okay, to this side. Okay, so that means I'm going to integrate along the x-axis. So my x, what is going to be my lower bound, is going to be this side. So it's going to be this line, right? And it's going to be 0. What about the upper bound? It's going to be this curve, and that is 1 minus y squared. And since I'm integrating with respect to x, since my order, I'm going to start with x first. I'm going to just choose the endpoints for y. So y here is going to be -1 and +1. If you don't want to use this order of integration, you can do so, but make sure that your y is subject to the formula here. Okay, so let us calculate the volume, the divergence. Okay, so So I'm going to write that the flux is going to be equal to the triple integral. We have negative 1 to 1, and we have 0 to 1 minus y squared, and we have 0 to 2x, and we have the divergence 2y plus 2. And I'm going to write it dz, and this is dy. Okay, this is dx, sorry, and I'm going to have dy. Okay, so make sure that your outer limits doesn't contain any variable. Okay, and if you are integrating with respect to z, make sure that your limits don't contain z. If you're integrating with respect to x, your limits should not have x. If your limits have the same variable, which is the same which you're integrating with respect to, that means that you have done something something is really bad, right? Okay, so now let's integrate with respect to z. We don't have any z variable here, so I'm going to write from negative 1 to 1, from 0 to 1 minus y squared, and I'm going to have 2y plus 2, and I'm going to write z here from 0 to 2x. I'm going to have dx dy. If we say upper bound minus lower bound, like what we always do, we're going to have negative 1 to 1, 0 to 1 minus y squared. We're going to have 2x, 2y plus 2, and we're going to have dx dy. I'm not going to expand y because I don't have any x variable here, so I'm just going to integrate with respect to x. So if I do that, I'm going to get negative 1 1, and I'm going to have 2x squared over 2. I'm going to have 2y plus 2, my limits from 0 to 1 minus y squared dy. Okay, and what I'm going to do, I'm going to say upper bound minus lower bound, and upper bound minus lower bound, what's going to be the answer for that? Okay, so it's going to be negative 1 to 1. They're going to write 2 where there's x. So where there's x, we're going to write 1 minus y squared. It's going to be, so 2 divided by 2. I think I can just divide 2 here, so that means I'm not going to need the 2 here. So I'm only going to need x squared, and x is 1 minus y squared times 2y plus 2. And 1 minus y squared, remember, this is x squared, and x is equal to 1 minus y squared, so we're going to need to put a 2 here. Okay, like this. Okay, and I'm going to write dy here. And now it's our job to expand. So I'm not going to expand, because if I do that, this video is going to take about 1 hour. So I'm just going to show you the expanded answer. So I'm going to have negative 1 to 1, and what we're going to have, 2y to the power 5 plus 2x to the power 4 minus 4x to the power 3 minus 4x to the power 2 plus 2x plus 2, and you're going to have, okay, this should be y. Okay, since we're in y, so this is y, and first of that, this is y. Okay, and now I'm going to integrate with respect to y. So I'm going to have 2y to the power 6 over 6 plus 2y to the power 5 over 5 minus 4y to the power 4 divided by 4 minus 4y to the power 3 divided by 4 plus 2y to the power 2 over 2 plus 2y, and my limits from negative 1 to 1. Okay, and we're going to get 1/3 right here. We're going to have 1 here. We're also going to have, so if we integrate here, if we add power, we're going to get 5, and here we're going to get 5. So that means nothing is going to cancel out here, but you can cancel out right here, right here, right here. So let me just write a clear one. we have 1/3 y to the power 6 plus 2 over 5 y to the power 5 minus 4 over 5 y to the power 5 minus y to the power 3 plus y squared plus 2y from -1 to -1. Okay, so if we say upper bound minus lower bound, what are we going to get? We're going to get 32 over 15. So that is going to be your total outward flux for this, for the wall solid. Okay, so now we want to move to this side. We have surface 1, surface 2, surface 3. Okay, so you are going to start with the surface which you want, and I've said that I'll do these things first. Okay, so on the right hand side, I'm going to start with the base. Okay, so the base of the solid, or the base of that half of the same cylinder. Okay, so the base of the same cylinder, we've said the equation of the base. We're now in the xy plane, both the base, we don't have any z, so we have something like this. Okay, so this is the graph of 1 minus y squared. Okay, so we have something like this, and we have 1 here, and we have -1 here, and we have +1 here. Okay, so what we need to do, since it's the base, that means the outward is going to be below. So if it is below, that means the normal is going to be equal to k. So that means the normal is going to be -k, right? That is going to be the normal, because the opposite is going to be on the -x direction. Okay, so now for the normal, we have k. Now let's calculate f dot n. So for f dot n, as for f, we have our vector field, and our vector field, this is our vector field. And I'm going to write for the I component, we have y plus z. Let me just write it here. And for the j component, we have y squared, and for the z component, we have 2z times the normal. And what is -k? So -k is 0, 0, -1, like this one. And if we do that, what we're going to get, we're going to have 0, 0, we're going to have -2z right here. So I said we're at the base. So if we're at the base, we're just going to integrate with respect to x and y. Okay, so we're going to, our integral is going to look like this. The double integral of -2z dy dx or dx dy. Okay, so we're going to have, I'm going to choose dx dy, because why? Because this is what we've used when we calculated our flux using the divergence theorem. So we're going to have our y from -1 to 1, and our x from 0 to 1 minus y squared, -2. And what is z? We've said it's the base, so z is going to be equal to 0. Going to have dy dx, so the answer is going to be 0. Okay, and this one is for the base, which I'm going to call surface number 1. Okay, like this. Now what I'm going to do, I'm going to move on to the slant surface. Okay, or to the plane z is equal to 1. Okay, so for the plane z is equal to 1, which is going to be surface number 2, z is equal to, but right here we're not given the normal, and our normal is not exact. Why? Because we have something like this. Let me sketch the z is equal to x plane. So the z is equal to x plane is going to look like this. Z is equal to 2x. So this is going to be z, and this is going to be x. Okay, so this is the normal. So what is going to happen here? So our normal is going to be something that is perpendicular and something like this. So you have to calculate the normal right here, the normal right here, the normal right here. So our normal is going to be in form of plane. It's going to be a plane, right? Okay, so how are we going to do that? Okay, so we know that the formula for the normal, what is the formula for the normal? So the formula for the normal is going to be the gradient of a function g divided by the magnitude of that gradient. Okay, like this. Okay, and we're given that our plane is 2x. So if our plane is 2x, that means z is equals to 2x. Let's create a function g of x, y, and z, and this is going to be 2x minus z. Okay, so you have to make sure that the coefficient of z is 1. Okay, the sign doesn't matter. Okay, so let's start by the gradient of g. So the gradient of g is going to be the partial x of g. I'm going to put I plus partial y of g. I'm going to put j plus partial z of g, and I'm going to put k. Okay, so if you do that, we're going to see the partial of x here, of g with respect to x. We're going to get 2, right? I, and for y, you're going to get 0, j, and for z, you're going to get negative k. Okay. What about the magnitude of the gradient? So I'm going to see, I'm going to get the magnitude of g. You're going to get 2 squared plus 0 squared plus minus 1 squared, and it's under the square root, right? Like this, and we're going to get root 5. So this means the normal is equal to 2i plus negative k divided by root 5. Okay, but according to our formula, you say that the formula for the surface integrals, so surface 2, is going to be the double integral of n ds. So this is a big S. Okay, so what we need a small s right here. So to remove this big S, it has got a formula. So we're going to say ds is equal to zx squared zy squared plus 1. Okay, like this. As you can see, all this under this zx. So zx, this means that we are differentiating x z with respect to x. So if we do that here, you're going to see we're going to get 2 squared plus 0 plus 1, and we're going to get root 5. So as you can see, our ds will be always equivalent to the magnitude of the gradient, magnitude of g. Okay, so now we have this. So according to our formula, we're going to say S2 is equals to, for F, we know our vector field. So our vector field is y plus z, and we're going to have y squared here, and we have 2z here. Okay, times, and I'm going to write my gradient. It's going to be 2i minus k divided by root 5 times ds. So for ds is going to be root 5. I'm going to put my double integral. And so this is the region. I'm going to call this region D. Okay, so as you can see, root ds and magnitude of g will cancel out. Okay, if they don't cancel, that means you've made a mistake somewhere. Okay, so from here we're going to say f, we're going to put our vector field, and n, which is our normal, this is our normal, okay, which is this one, and ds. And after that, you're going to see that the magnitude of ds and the magnitude okay, so from here we're going to put f times the dot product of n, which is the normal, which is right here, times ds. Okay, so we're going to see that the magnitude of n of our normal, the denominator of our normal, which is root 5, is going to cancel out with the ds. Okay, so now let's evaluate the answer. So we're going to have, so our surface is going to range, as you can see, our surface, this is going to be our surface. So this is 2x. Okay, but it has got a limit, because the cylinder, because of our cylinder x, the maximum limit for x is going to be 1. so the maximum here is going to be 1. So let's put our limit right here. So x from 0 to 1 and z from 0 to 2x. Our normal, if we multiply I component times the I component, we're going to get 2y here plus z plus 0 minus 2z, and we're going to have dz dx. So as you can see, okay, I think if we multiply this, we're going to get 2 here, 2y and 2z. So z and z will go out, and we're going to be left with 2y dz dx, and this is going to be from 0 to 1, and we're going to have 2y z, okay, from 0 to 2x. Okay, so now let's finish here. So if we finish here, we're going to put our limits. So we're going to have 2, but what is y? So y, we know that from our limits, we know that y is equal, okay, before doing that, let me just write here from 0 to 1, we're going to have 2y times 2x. I'm not going to put 0. What's going to be 0? So there's no need to put 0. Okay, so I'm going to continue right here. We're told from our limits that we have a cylinder with wall x equals to 1 minus y squared. That means y is equal to 1 minus x. Okay, so from here, to evaluate the surface, to evaluate this integral, we're going to, let me just write surface number 2. Okay, so we're going to have the integral from 0 to 2, from 0 to 1, and we're going to have 2 times 2, that is going to be 4x, the square root of 1. So this is going to be minus x. It's not going to be a positive. So this one is a negative. Okay, and we're going to write dx here. So to solve this, we're going to use substitution. You can say let 1 minus x be equal to u, and that means du dx is going to be negative 1, and the dx is going to be negative du. Okay, so dx is going to be negative du. Okay, so this is dx. Okay, after doing that, we're going to say our limits from 0 to 1, and now we can pull out 4 since it's a constant, and for x right here only have x, so that means x is going to be 1 minus u, and here I'm going to write u to the power half. Okay, and for dx we're just going to write negative du, and we're going to solve here. We're going to evaluate here. So this is 401, and what is going to happen here? Okay, so we're going to have u to the power 1 half minus, so this is u to the power 1 and u to the power 1 half, so it's going to have u to the power 3 over 2 du, right? And we have our negative. Let me just put my negative here. Okay, so you can just say u from 0 to 1, we're going to have u 3 over 2 minus u to the power 1 half du. Okay, if we integrate, going to add the power. So if we say 3 remainder 2 plus 1, okay, so we're going to have 5 remainder 2, or 2 comma 5. So we're going to have negative 4 here. I have u to the power 2 comma 5 divided by 2 comma 5 minus, and they are going to have u to the power 1 comma 5 divided by 1 comma 5. Okay, from 0 to 1, like this. Okay, but you know what is our u? This goes to 1 minus 6, so it's going to be minus 4. 1 minus x to the power 2,5 over 2,5 minus 1 minus x to the power 1,5 over 1,5. And our limit 0 to 1. Okay, so what is going to be the answer? Okay, so the answer is going to be, if we evaluate here, if we say upper bound minus lower bound, okay, so we no longer have a negative here, since they split the negative right here, it's going to be positive. So the answer is going to be 16 over 15, right? That is going to be your answer if you say upper bound minus lower bound. Okay, so if we move to the surface number 3, which is the cylindrical surface. Okay, so for the cylindrical surface, like always, we're going to start by calculating the normal. Okay, so the normal of this equation. Okay, so I want to calculate the normal of this equation. So let's calculate the normal. The normal is going to be, let's write the equation first. X equals to 1 minus y squared. That means our g of x, y, and z is going to be x plus 2y minus 1. Okay, minus 1. And let's calculate the gradient. Okay, so for the gradient, it's going to be normal, it's going to be the gradient of g over the magnitude of g. Okay, so this is going to be equal to 1i plus 2j, but we have 2y since this is y squared. Okay, so I'm going to have 2y here, so let me write 2yj, okay, divided by, and we're going to say 1 plus 4 2y, that's going to be 4y squared plus 1. Okay, and this means that, this also means that ds is also going to be 1, so that will become 2 plus 4y squared. I think I've shown you how. Okay, so I'm going to work it out here. Surface number 3, double integral d fn ds. Okay, so now we have our fn. So I'm going to say the normal. What is going to be the normal? F our vector field. So our vector field, it's y plus z on the I component, y squared on the j component, and 2z on the k component, times the normal. What is the normal? Normal, we have 1 plus 2y, and we have 0. Okay, and we said ds is going to cancel out with 2 plus 4y squared over 2 plus 4y squared. I'm going to have the double integral here, d, and I'm going to have a small letter ds. Okay, so what is going to happen? I'm going to have 0 from negative 1 to 1, and 0, 1 minus y squared. Okay, since it's a circular, I'm not going to use cylindrical coordinates. I think I've told you the reason why. And here, this one and this one, so I'm going to have y plus z here plus 2y to the power 3, and I'm going to have dy dx dy. Okay, we know z. What is z? We know z. We're told that z is equals to 2x, so I'm going to have 2x plus 2y to the power 3 dx dy from negative 1 to 1. And what about here? Going to have yx plus x squared, right, plus 2y to the power 3x. 0, 1 minus y squared dy. Okay, so let's just put y squared here. Okay, so we're going to have from 1, we're going to have y 1 minus y squared plus 1 minus y squared to the power 2 plus 2 y to the power 3, 1 minus y squared, going to have dy. Okay, and if you integrate here, what are you going to get? Okay, so let's try to expand. So from negative 1 to 1, going to have y minus y to the power 3 plus 1 minus 2y, 2 plus y to the power 4 plus 2y to the power 3 minus 2y to the power 2 dy. And we're going to have y squared over 2 minus y to the power 4 over 4 plus y minus 2y to the power 3 over 3 plus y to the power 5 over 5 plus 2y to the power 4 over 4 minus 2y to the power 3 over 3. Our ranges from negative 1 to 1. So if you evaluate these, are going to get 16 over 32. Okay, so now what is our total flux? So our total flux is going to be S1 plus S2 plus S3. Okay, so for S1, what do we have? 0. S2, we have 16 over 30, 16, sorry, it's 16 over 15 here. We have 16 over 15. For S2, we have also 16 over 15. And this is going to give us 32 over 15. Like what we get when we use the divergence theorem. So now we can now say the theorem is verified. Okay, so don't forget to subscribe, guys, please.